I had this Dan Bullard, retired electronics engineer, on the front deck of my houseboat again. We've had snow. We got some snow last night. Not a lot, but some of it's left over from a couple days ago. And you can hear the cars really good because there's no leaves on the trees. I thought I'd back up a little bit and talk about automatic test. And I want to tell you about how I got in the automatic test industry, but finish off with a talk about memory tests and algorithmic pattern generators. And this thing's good. And this is my gift from my daughter, Samantha, and her daughters. Years ago, I was teaching at a school back in Campbell, California, called Technical Training Center. And Technical Training Center was a low-end school. That's where I mentioned I had a student from MIT in it. You know, it was friggin' wild. But it was a great school, and I went in there. I was in there for 2 years, and I was Dean of Education after a year. Dean of Education. Okay. Now, I'd been in the Navy for 6 years before that. So Dean of Education was pretty good. And I got a call out of the fucking blue from, now this is, let me back up a bit. I went to my 10th high school reunion and I met my friend Rob Hopp, who we had a kind of a falling out in high school, but we made up in the 10th anniversary. And so we went, we're talking about how much money you make. And I was making at TTC, I was making like $23,000 a year maybe. And we were talking, and he worked for a phone company, a local phone company. He worked in electronics too. And he said, "Isn't it great when you start making over $30,000? I'm like, "Yeah, it's great." I'm like, I got to find a way to make over $30,000. And so what I did was, I just, I kept working at TTC, and the boss loved me. And I mean, I didn't have to teach. I was a trainer, I was a teacher, but I didn't have to teach. I was in charge of the whole educational staff. I fired people. He hired them, I fired them. But it was kind of cool. But out of the blue, GenRad called me up. GenRad, General Radio Company. And they called me up, and they wanted to interview me over something, a training position. And so when I went and interviewed with Paul Emmett, I said, "Why did you call me?" And he says, "Because some of your students, we had a job fair, and some of your students were here, and we asked them if they knew a good trainer. And they said, yeah, our trainer, our teacher is really good." And so out of the blue, my students recommended me for a job at GenRad, and so I got a job at GenRad. And they asked how much you want. I said, "How's about $30,000 a year?" And they said, "Okay, no problem." And boom, I was in. And so I left TTC, but I really liked TTC, but there was not any money in it. And I was going to make more money in the long run in automatic test anyway. So I took this job at GenRad, and I was a trainer for the maintenance. And I worked with this guy who he taught the class, the maintenance class. He was an English guy, had a degree, and his big thing was he had schematics of the whole tester. And apparently this was the way you did things back then. Sorry, my legs are getting burned by the heater. And so he ran the students through the schematics of all the boards, and it was a big machine. This is a picture of a GR16. It was a big machine, up to 144 digital pins. It had an APG. It had 4K of pattern memory, optionally up to 8K of pattern memory. It also later got an additional, I think, 256K of pattern memory with the PTT. So it was kind of an upgrade. But Paul taught them the schematics. It was terrible. And then he would put bugs in the system, and they were supposed to find them, and they never found them. his training wasn't doing the job. And so I got in there and I started helping him out, right? I learned the system and then I started helping him out. And I took it over and he ended up getting another job doing something else. After we went to high-low school. We went to high-low school, which was another division of GenRad that they had bought. And it was about digital simulating digital parts. But the GenRad GR16 was meant for testing digital parts. No mixed signal at all. Now, the GR16, I mean, I could tell you tons about it. It was a great tester. 40 megahertz, it started out 33 megahertz, and their only stumbling block there was having a TPP that would run over 33 megahertz. And so they built a TPP, test pattern processor, TPP-204. And the TPP-204, they gave it to me and they said, you have to learn this brand new thing and you have to teach our service engineers and the customers on the TPP-204, and you're going to have to impress a guy named, I think it was Mike 10K, and he was a son of a bitch. Apparently, they told me he was a son of a bitch. He would roast me alive if I got anything wrong. So I gave the class. I developed the class on the TPP-204, which included the APG, and he had one negative comment about my whole thing. I had misinterpreted one thing, and he straightened me out on that, and otherwise he loved the class. And so and then they took all the stuff that I wrote about the TPP, and one of the contractors took it and published it in a book that he got paid for as a contractor. And he had no regrets, and I couldn't believe it. People were stealing from me way back then. So he stole from me and got paid money for my writing. Terrible. Anyway, the GenRad APG was based on Jim Healy's book, and I think I got a copy of it here. I did a video on Jim Healy's book. Great book. Jim Healy, I think he was a good guy. I worked for him directly. I think by the time I got into GenRad, he'd already left or gotten close to already leaving to go to LTX. But eventually he became president of Credence. And he was a nice guy. He was, I don't know if he was, one of those guys that would fire you in an elevator like Steve Jobs would do, but, he was okay and he knew what he was talking about. And so the APG was designed by Jim Healy. He was the guy who designed it. He came from Fairchild. And so the APG, and here's where we get the APG, the algorithmic pattern generator, it's a way to test memories. Okay, now most memories are square, presumably. You can assume they're square, but they're probably not. And the APG had, it was a bunch of boards, a bunch of circuit boards. And in the circuit boards, there was an X address generator and a Y address generator and a Z address generator if you wanted it. And the Z had X and Y, X for row, Y for column, and then Z was for the refresh address if you wanted one. And you didn't have to. Refresh address for dynamic RAMs and stuff like that. Now, I didn't know a thing about it, and nobody else there at GenRad knew about the APG. But they asked me to look into it, and I said, okay, I'm an idiot who signed up for mixed signal, So it was kind of stupid, but I decided I would learn. And I had one of the guys I worked with, Frank Levine, he was asked if he would do it. He taught applications. See, I only taught maintenance. Then later I picked up applications. But Frank Levine refused to teach the APG because he said he wasn't a test engineer. I'm like, it doesn't matter, Frank. This is your job. You got to do it. You got to feed your kid. You got to feed your wife. Got to put a roof over your head. apparently he wasn't so motivated. It didn't matter. He was going to move into apps anyway and leave me and far in the dust. He's retired now apparently, and he's retired on Social Security, making a little more than I am. He's probably making like $400 or $500 a month more than I am, and I'm doing pretty goddamn good. So he's making good money. So it had X, Y, and Z pattern generator, and it had a data register. And it also had like a serial data generator and for scan, if you've ever done with stuff with scan, and they do it in Intel and other places. They use scan. But let's talk about the X and Y address registers. X and Y is pretty easy. To test a memory, you have to have an X address register and a Y address register so you can address the rows and columns and get through this memory. And you have to have a data register that is 8 bits or more wide so you can talk to the individual data bits. You can talk to a single bit or 2 bits or 4 bits or 6 bits or 8 bits or 16 bits. Generally, that's as high as it goes. So the data register is where you would put the data generation pattern. There was also a ROM pattern generator, so you could save the contents of a ROM into the ROM pattern generator, and then you can read out a ROM and make sure that everything was okay. Now, when you did that, you used 2 different opcodes. They had 1 and 0 for driving ones and zeros. They had H's, L's, and T's. H for testing for high, L for testing for low, and T for testing for tri-state. They also had other things, but more importantly, they had P's and D's. And a D code told the test pattern selector. The code told the TPS which way to flip it. So if it was any one of the other codes, 1 or 0, H, L, or T, whatever, it would just send that up to the formatter and off you go. And it would drive 1s and 0s to the part, or it would expect high and low or tri-state from the part, whatever you wanted. But if it was a P or D code, then it took the pattern generator data. So if it took, let's say you did a D code for drive, so it would take whatever the pattern generator bit that was assigned to it, like a 64-to-1 matrix for every pin. So every pin could choose any one of the 64 different resources out of the pattern generator, and then you could use it for driving a 1 or 0. So if the X address register was set up for all the address pins, you would send the X address on the cycles when you wanted to talk to the X address, which is the row address. Now, you could do that on the fly. So you would do like on a DRAM, which had multiplex address register, address bits, you would send the row and strobe RAS, and then you would send the column and strobe CAS. So you'd send the X address register with a bunch of Ds, then send the RAS signal, it would clock in the row address, then you would send the Y address register out with Ds in a different time set, and it would go to the column address, and there you go. It would get the column address locked in, and you get your data out if you're reading, or if you were writing, you could write the data in. And the data, again, came from either the 1s and 0s, or H's and L's, or T's, or it came from the data register, or from the ROM pattern generator. And so what you would do in a RAM test, and here's what I'm going to show you this RAM test. Now here it is, it's a square memory, or it doesn't have to be. It can be any kind of memory. But I set up this thing to be a square memory, and I have the X address register and the Y address register. The X controls the row, Y controls the column. And this is an 8x8 memory, but I shortened it to be 4x4 so I didn't have to simulate the whole stupid thing. So I have these opcodes. Now I just made this up, but this is based on what I've worked on APGs on the GenRad, on the Schlumberger and on the Nextest. And I also decompiled some Japanese tester. I knew what they were doing. They were using the APG to test a DAC, right? Because you can use the X address register or the Y address register, whichever one, to increment up and make a ramp to test the DAC. And that's what they were doing. So I just used that because I had to transfer a program from a Japanese tester to MT for, it's empty, don't ask. But it took them forever to come up with the mixed signal version of that. But anyway, so for the DAC, I had to send the row address as the address or the data to the ramp to test the DAC. But anyway, back to this other APG thing. So I'm going to send the row address during a RAS cycle, then I'm going to send the column address during a CAS cycle, and then I would look at the data. Now this memory I'm just showing, we don't worry about row address or column address. We just send out the row and column address. And I don't show you the P's and D's or any of that. Now we start off with the X address register at 0, X max at 1-1, which is a 3. Right? 1-1 is a 3, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so I'm going to start the X address register at 0, 0. I'm going to start the Y address register at 0, 0. And then every cycle, I'm going to say increment YR. So if I start at 0, it does this, it's post-processing. So increment YR, so I'm going to do everything with a 0 in it. And then I'm going to increment the Y register after it's done. And so I'm going to go from 0 to 1. So that'll move me over to the next column. If equal YR, Y max. I'm not there yet. Okay. So first time I'm going to send a 0, 0 to it. And for the data register, I'm going to send whatever's in data XOR'd with XY and XR. So if the data register is set for 0, which I think it is in this case, so if I send a 0 XOR'd with a 0, what's 0 XOR'd with 0? It's 0, right? If the data register is not equal to the bit at XOR YR, okay, so if you take XOR and YR and you exclusively OR them, and the DR register is not equal to that thing, then you're going to fail. Okay, so we're putting in a 0. We're going to read back a 0, hopefully. And then, if everything's okay, we're going to go to the next one. So we're going to increment the Y register again. So we're going to go to a 1. We're not there yet. If we say if equal YR, Y max, we're not going to do that stuff yet. And then we're going to send the data register, which is the XOR of YR and XR. But this time, the YR is 1, the XR is 0, so we're going to send a 1. So we're going to write a 1 into that cell. So we started with a 0, now we write a 1. Then we go to the next address. If it doesn't read back right, we fail it. Okay, we do an increment YR, so now we're up to 2 in the Y register. Still at 0 with the X register. 2 XOR'd with 0. The data register is 0, so everything's fine. So we go 0, 1, 0. And then, if that 0 doesn't read back to 0, we fail it. Okay. Now we increment again. Increment YR. So now the Y register's up to 3. That's a 1, 1. We did 0, 0, 0, 1, 1, 0, 1, 1. Now we're doing 1, 1, which is a 3, digitally. We do a 3. The DR is inverted because XOR says YR is 1, 1, but the XR is 0, 0. The LSB is XOR'd, and that's the data register value that we use. sorry, we get 1. So we get 0, 1, 0, 1. Now, for the next one, next cycle, increment YR if equal YR Y max. Whoa. If YR is equal to Y max, which it is now, it's 3, and so Y max is 3, YR is 3, and so the if equal goes through, YR is reset to 0 and increment the XR. So I've gone through all 4 columns. Now I'm going to go to the next Y or the next X address. If XR is equal to X max, it's not. And don't worry about that yet. Okay. The data register. Where's the data register? Remember at 0, 0, it was at a XOR of X, YR and XR. Okay, but now XR is 1. So now YR is 0, XR is 1, the XOR of that is 1, so we write this next bit to a 1. And what that does for you is it gives you a surround disturb kind of thing, assuming that these bits are topologically close. Now that's not necessarily true. It could be that it's designed some other way. If you know what the topological scrambling of the bits is, you can program that into the topological scrambler, which is called a topo scrambler. So if you program the scrambling algorithm into the topo scrambler, then YR, those 2 bits may be together physically, they may not. And you want to find out if we get crosstalk between those 2 bits. So you try XORing them, but I'm just assuming here that there's no topological scrambling. So address the first row 0, was 0, 1, 0, 1, and now this row is going to be 1, 0, 1, 0. Okay, let's go on. Okay, the next step I do increment YR. So if equal YR Y max, it's not. The Y register is only 1. So we've got a 1 in the Y register, a 1 in the X register. That's great. The XOR of 1 and 1 is 0. So this bit gets set to 0 and then gets tested for 0 with the statement if equal DR blah blah blah. Okay, or if not equal, sorry. If not equal DR and so on. Okay, so we did 0, 1, 0, 1 in the first row, then 1, 0, 1, 0 in the next row. Okay, so we go through all 3 of those, all 4 of those, and then once YR gets to 3, so we've got 1 in XR, 3 in YR, if equal YR to Y max, so Y is going to flip over, isn't it? It's going to go to 0, 0 again. So the Y register goes to 0, the X register increments and goes to 2. So now we're going to do the Y register out there to location 0, that's column 0, the X register to location 2, and if we XOR the X register and the Y register, then we get 0 again. So we have 0, 1, 0, 1, then 1, 0, 1, 0, now 0, 1, 0, 1 for the next row, so row 2. Okay, one more. We finally increment YR again. So YR is again 0, XR is now 3. We haven't got to the point where XR needs to be flipped yet. YR is 0, XR is 3. If we exclusively OR XR and YR, it's 1 again. So now we do 1, 0, 1, 0. So we've got 0101, 1010, 0101, and 1010. So what does that do for us now? Once we get to YR being 3, we go if equal YR equal to Y max, YR is equal to 0. Increment XR. If equal XR is equal to X max, and equal YR Y max, realize that there was a point where the XR was 3, but it didn't matter because we didn't get to this point because the XR was not all the way tested out. So we do the first row, the second row, the third row, the fourth row. Now, when we're at the last bit of the last row, we program YR to 0, XR to 0, and we go to the next. Then we do, and I don't want to go through all the crap, but just notice one thing. Between these two statements, we have the first one, DR is equal to XOR of YR and XR. But in the next one, we do DR is equal to not XOR YR and XR. So we're going to take that checkerboard pattern and flip it over. So it's going to go 1010, 0101, 1010, 0101, and then we're going to be done. This is the finish. Now this is a checkerboard pattern. Now there's a lot of patterns you can do. This is a really simple pattern, and I just did it for fun. I mean, I can't imagine doing another one that's more complicated than that. A walking ones pattern. I wrote a walking ones pattern for the GenRad as an example, but it's a terribly wasteful pattern. You don't want to use walking ones, or even marching ones. You don't want to do those. For testing memories, you have to talk to the engineer in charge of your product to find out what kind of pattern they want to use. Now, you can have the APG inside the tester, or it can be inside the chip. When I was at Intel, that's something they were doing with the L2 cache. With the GenRad, the Schlumberger was what they were using. Now the Schlumberger had a double APG. It had 2 of them. Now their APG could only run at 50 megahertz. Remember, the GenRad could only run at 40 megahertz, which that's not bad. But the Schlumberger APG could run at 50 megahertz. But what they did, those guys were so fucking smart. When I criticized like Credence and those guys, Nextest, Schlumberger was extremely intelligent. How do you think I came up with this cool animation? I was doing animations on all kinds of other things, like the Apple or the Windows thing, but my teacher at Schlumberger was a genius, and he completely animated the sequencer per pin functionality of the Schlumberger using animated GIFs. And I was so impressed, and so I thought the very least I could do is an animated GIF that showed how to do an APG. But on that tester, they had their APGs could only run at 50 megahertz, but you could have 2 of them running together. And because they had an option for not just to increment the XR, but increment the XR by 2, so they could run them in tandem. So you could run an APG at twice 50 megahertz, 100 megahertz, twice the speed, because you would flip between one APG and the other. So you're actually able, because you would increment by 2, so you start the X register at 00000, and you start the Y register at 00000. But on the other one, you set them for 00000 and 00001, and set the Y register for 1. So now, the X register would take care of the even cycles, and the Y register, I'm sorry, not the Y, the other APG would take care of the odd addresses. It was really cool. So each one of them incremented by 2 each time. It was fucking cool. Now, I've been out of memory chess for a long time. So, don't take everything that I say with a grain. I mean, take it with a grain of salt. But be aware that this is how you test a memory. You don't use a memory to test a memory. That is the stupidest thing you can do. I've got a buddy who works for, and I won't mention his name, but I've mentioned him many times in previous things. The tester that he talks about, that he sells, has no APG, even though it's also meant for memory. It should have an APG, but they think they have enough memory that you don't need an APG. Bullshit. You need an APG. An APG is the way to go. It's an algorithmic method of testing memories, and it's a smart way to do it. For the Y register, and there's a section on that, I think I give you the link to the web page that talks about my APG course, and I did a thing in there where I let you also do a learn, and I do a ROM, and also a refresh. So you can do a refresh with the Y register, and they normally don't do that with dynamic RAM, and who knows if anybody's even using dynamic RAM anymore. But with DRAM, if you want to refresh it, you simply call up a subroutine. Anyway, I think it's getting close to either snowing or raining again, so I'm going to go. My scarf really helped keep me from freezing, but it's going to get cold and rainy, so I'm going to go. Anyway, this is Dan Bullard from the river. Merry Christmas and Happy New Year.